So this question appeared in IIT-JAM 2019 examination. The question is the Fermi-Dirac distribution function, that is NE, is where kV is the Boltzmann constant, T is the temperature, and EF is the Fermi energy here. Okay, so before we make a final choice here, let's try to understand the general distribution function. Okay, so here the general distribution function for any kind of statistics that can be written as NE, that is equal to, sometime it's also denoted by letter F, okay, and this is equal to 1 divided by exponential E minus EF upon kVT plus A. So depending upon the value of A, we will have three different cases. Okay, so if A is equal to 0, so when A equal to 0, then we obtain the distribution function for Maxwell-Boltzmann statistics. Okay, and when A, this is equal to plus 1, the distribution function that we obtain, that's valid for the Fermi-Dirac statistics. Okay, and when A, this is equal to minus 1, the expression or the distribution function that we obtain, that's valid for the Bose-Einstein statistics. Okay, so that means when A is equal to plus 1, the distribution function, it reduces to NE, and this is written as F of Ft. Okay, where Fd, it stands for Fermi-Dirac. Okay, this is equal to 1 divided by exponential E minus EF by kVT plus 1. So therefore the correct choice is C here. The question is isothermal compressibility is given by. Okay, so before we arrive at the final conclusion, let's try to understand. So in general, we in thermodynamics we learn about 4 different quantities. So what are those 4 different quantities? The first is isothermal compressibility. Isothermal compressibility. Okay, and this is denoted by letter kappa T. Okay, and this is equal to 1 by V dV by dP. Sorry, it is dV by dP, and at constant temperature, because it's a isothermal bus. Now when we increase the pressure, okay, suppose we are increasing the pressure, then what happens to a system? Suppose it's a gaseous system, then volume will be reduced. So this implies delta V will be a negative quantity. So because the delta P here, it's a positive quantity when we are increasing it, and there will be a corresponding reduction in the volume. So this will make this quantity as a negative quantity. Therefore, to make it a positive quantity, a negative sign is introduced here. Okay, so similar to the isothermal compressibility, there is another quantity which we call as the adiabatic compressibility. So let's try to understand the difference between these two. Adiabatic compressibility. And this quantity, it is denoted by kappa and S, because in a reversible adiabatic process entropy is fixed. Okay, so kappa S similar to kappa T, it can be defined as with negative sign. The reason for the negative sign, it's same as I mentioned earlier. So minus 1 by V dV upon dP, but now the constraint is of constant entropy. So that is the adiabatic compressibility. Similarly, we have 2 more quantities. Okay, although it's not asked in this question, but there is a very simple way to remember all these 4 quantities. Okay, so the third quantity is, it is isobaric expansivity. Okay, isobaric expansivity. Okay, and it is denoted by alpha P. Okay, so what is alpha P? So alpha P, again, it is the fractional change in volume, that is 1 by V delta V. okay, and then isobaric expansion. So expansion occurs when you change the temperature, so that's why in the denominator we will have a temperature here, and the condition is constraint is of constant pressure, okay. And then the fourth one is adiabatic compressibility. Expansivity, not compressibility, but expansivity, and it is denoted by alpha s. So alpha s, this is given by alpha s, this is equal to fractional change in volume 1 by v delta v with respect to change in temperature, and the condition is adiabatic, okay. So this one. Now the question is how we are going to remember all these four quantities. So the only thing that you have to remember, it is the fractional change in volume. So that is fractional change in volume, which is equal to 1 by v and multiply by delta v. Now if someone asks, it is the isothermal compression, isothermal compression. So compression is with respect to pressure, so in the denominator put the change in pressure, and the condition is isothermal, so put the constraint of constant temperature, and this is equal to kappa T. Similarly, when the constraint is of constant, the question is adiabatic compressibility. So again, the basic expression it's going to stay the fixed, but then you have to simply change the constraint of constant temperature with constraint of constant entropy. Then we will obtain adiabatic compressibility here. And for the expansivity, again the 1 by b, it's a fractional change in volume, right? It's a fractional change in volume. Then expansion occurs with respect to temperature, then put temperature in the denominator, okay, and then put the desired constraint. If it is isobaric, put pressure here, and if it is adiabatic expansivity, then instead of pressure put the constraint of constant entropy. So this way we can obtain all these four expression in a very simple manner, okay. So here the right option for the isothermal compressibility, it is C here. So let's continue with the next question. The statement is in a heat engine based on Carnot cycle, the heat is added to the working substance at constant, okay. So let's try to understand how the heat is added to the working substance. So if we recall what we have learned in thermodynamics, okay, in a Carnot heat engine we are having a source at certain temperature T1, and we are having another source which in fact we call as sink basically, okay, at temperature T2, which is smaller than temperature T1, and in between we represents a working substance, okay, like this. And here the working substance, it takes Q1 amount of heat, okay, Q1 amount of heat from the reservoir which is temperature T1, and then it perform some amount of work, and then at the same time it also rejects certain amount of heat to the reservoir at lower temperature. So here one can write W, that is equal to Q1 minus Q2, okay. So working substance in principle, it undergoes undergoes through a cycle which consists of two reversible isothermal processes, okay, and also it consists of two reversible and adiabatic processes, okay. So in general we draw the Carnot cycle on a PV diagram like this, P versus V, okay. So the process starts from a certain point here, let's say this is point A and this is point B. This is an expansion, okay, and then again another expansion but with another slope, okay, and then it comes to the point C here, and then it comes back from here C to D like this, okay. It's compression basically, and then from D to A another compression, and then finally the working substance reaches as the same starting point, okay. So here this way a complete cycle is the cycle is completed here. So here during this process A to B, this is basically a isothermal expansion. So here during this process a Q1 amount of heat it is added to the working substance at temperature T1. Okay, so at temperature T1 here. Okay, why we need heat here? Because when the expansion it is taking place at constant temperature. Okay, so for expansion the gas has to perform some sort of work. Okay, so that means to keep the temperature of the gas constant we have to supply heat externally to keep its temperature constant. So therefore we got the answer from here. In a heat engine based on a Carnot cycle, the heat is added to the working substance at constant temperature. So C is the correct option here. So this question is based upon free expansion of the ideal gas. Okay, so the statement is, during free expansion of an ideal gas under adiabatic condition, the internal energy of the gas decreases, initially decreases and then increases, and then option D is remains constant. So first let's try to understand what is the free expansion. So when we talk about the free expansion of an ideal gas, so it needs to satisfy certain condition. Okay, let's consider a container which is divided into two equal halves. It's not necessary that the container should be divided into two equal halves. Okay, but just for the sake of simplicity we are assuming it. So we are having a container which is thermally isolated. Okay, we are having a isolation wall between the system which we are talking about and the surrounding. Okay, so this is an adiabatic wall basically, you can say. Okay, and the next condition for the free expansion need to be satisfied. So here we have to create the vacuum. Okay, and we are having gas molecule only in this side. Okay, we are having gas molecule here. Okay, at certain pressure P, and let's say the volume of this half part is V, and here also let's say the volume is B. Okay, and let's say the gas is at certain temperature T. Okay, so once these parameters they are fixed, so the equilibrium state of the gas that will be determined by these parameter. Okay, so once pressure, the volume of the gas and temperature they are fixed, so that means we can talk about the fixed internal energy of the gas molecule. Okay, now what we do is we are creating a very small hole here, so that the gas molecule which were earlier confined to volume V, now they can move through this orifice, and now they will come here. Okay, because of the concentration gradient, so gas molecule they will come here, and now they will be uniformly distributed in both half of the container. So earlier the gas was confined to volume B, and now the gas is confined to volume twice the initial value. So this will result in the reduction in the pressure from P to Py 2, because we are talking about an ideal gas. Then ideal gas it needs to satisfy this equation Pv is equal to RT. Okay, all the time this equation has to be satisfied. Okay, so therefore the pressure will reduce to half its initial value. Now the question is, what will happen to the total internal energy of the gas? So whether it's going to change or not. Okay, so let's try to understand. When this gas expands from the left half to the right half, because it's thermally isolated from the surrounding, so the gas doesn't lose any kind of energy. Okay, because here it's a this system it's completely thermally isolated. So here delta Q during this process it's 0. Now the question is, what is the work done by the gas? So if we take a look at the equation of the first law of thermodynamics, which says that delta U that is equal to delta Q minus delta W, where delta W is given by, or dW that is equal to P times dV. Now remember here, because it's the this process this is thermally isolated from the surrounding, so delta U this is 0 here. Now what about delta W? The gas is expanding, but what is the work done here? Because there is no interaction of the gas which is our system with the surrounding. So delta W here, this is the external work, it's not the internal work, this is the external work. okay, because there is no interaction of the gas with the surrounding. So delta W here also, this is equal to 0. Okay, so delta Q is also 0 because it's thermally insulated. Delta W is 0 because there is no external work done by the gas on the on the surrounding, or work done by the surrounding on the gas. So this implies that delta U, this is equal to 0, which implies that the final internal energy of the gas minus internal energy of the gas, that is equal to 0, which further says that UF, that is equal to UI. Okay, and this also implies that, so this is one of the important conclusion that's valid for the free expansion of the ideal gas. So because for an ideal gas, the internal energy, it's purely kinetic in nature, purely kinetic in nature, which further says that the final temperature of the gas, that is equal to initial temperature of the gas. So it's not only the internal energy which doesn't change during the free expansion of the ideal gas, but it's also the temperature which doesn't change. So that means here the correct option is D here. The internal energy of the gas, it remains constant, it doesn't change during the free expansion of the ideal gas. The statement is, in the given phase diagram of for a pure substance, region 1, 2, 3 and 4 respectively represent. So we have to identify these region from the given phase diagram, which is a diagram between pressure and temperature. Okay, so let's try to understand this, the phase diagram for first, and then we will figure out which one is the correct option. Here I am going to redraw it. So P versus T diagram. Okay, so here we are having a positive slope and then again a positive slope, and here as given in the diagram we are having a negative slope here. So for a pure substance, okay, we can call this as, here all these three lines they come together. For instance, when we are talking about the ice water system, because here the slope of this line, which is a dp by dt, which represents the change in pressure with respect to change in temperature. So for this line, the dp by dt, that is negative. Dp by dt, this is basically negative. Why? So when we are increasing the pressure, okay, so when we are increasing the pressure, basically, so here if you just take a look at this line, okay, so it's making a angle which is larger than 90 degree with respect to the vertical axis. Okay, so that's why it's a slope, it's negative. So this is basically a phase diagram for ice water system. Okay, now this, here we are having a solid phase, and here it is liquid phase, and here we have the vapor phase. Okay, so here let's mark the region. This is region 4 as given in the diagram. This is region 3, okay, and this is region 2. So this is the triple point basically. Okay, this is triple point, so where all these three curves they meet. Okay, so we also call this line as fusion curve. Okay, this is also called as fusion curve, and this line is called as this is the vaporization curve or vapor curve, and this is the sublimation curve, this one. So here along this line, so if we cross this boundary, so here the solid phase directly change into the vapor phase. Okay, so that's why this line is, this curve is called as sublimation curve also. Sublimation. Okay, so this is another important point marked here as the critical point here. So this is the critical point. Beyond this point one cannot distinguish. Okay, so beyond this point, if we are increasing the temperature further beyond this value, you can mark this as critical temperature. Okay, if we are further increasing the temperature beyond Tc, so there is no distinction between the vapor phase and the liquid phase here. Okay, so here we will have a only gaseous phase only. Okay, gaseous phase only. So now I think we have identified all the different phases here. So that means if I mark the region 1, region 2, region 3, and then region 4. Okay, so the way I remember this this phase diagram, so I write S, L, and G. Okay, or in another word, just okay, so I wrote it in a wrong way, S, L, and G, and then move in a clockwise manner. So solid, liquid, and then gaseous phase, solid, liquid, and then this vapor phase, you can say. Okay, so the first phase here it's marked as 1. It's above the critical point, so it is basically the gaseous phase or vapor phase, you can say gaseous phase, where there is no distinction between the liquid and vapor. Okay, and what is the region 2? It is the vapor. Region 2 here, it is the vapor phase. So region 2 vapor, and region 3 where it is, this is the liquid phase, and region 4 it is the solid phase. Okay, so let's check which one option is correct. So first of all, we are having gas here, and then vapor. The second phase is the vapor, the third it is liquid, and fourth is solid. So therefore B is the correct option here. The statement is, a red star having radius RR at temperature TR and a white star having radius RW at a temperature TW radiate the same total power. So it's given that both the stars which are at different temperature and having different radii, they are radiating the same total power. If these stars radiate as a perfect black body, then we have to find the correct relationship between their radii and the temperature. Okay, so let's try to understand this problem. The power radiated by a body at certain temperature, power radiated, that is given by, or that depends upon the area of that particular body and emissivity of that body, and then comes the Stephen constant sigma and T power 4, fourth power of the temperature. So because it's given in the question that the stars, they can be treated as black body, so here E will be unity for the black body, and we can replace this, we can rewrite this expression, the power radiated, if we denote by P. So A is the area of the body, area of the star here, so we can write it in terms of the radii, 4 pi r square sigma T power 4. So here it's a constant, sigma it's also constant, so that means in general we can write that power radiated by the star, that is proportional to square of radius and fourth power of the temperature. So let's call this as equation 1. So for the red star, the power radiated, if we denote the power radiated by the red star by PR, okay, and then that is proportional to R square, where the suffix R denotes that this is for the red star, okay, and then TR power 4, where TR is the temperature of the red star, TR power 4. Let's say this is equation 2. Similarly, we can write the expression for the power radiated by the white star, which is PW, and that is equal to the square of the radius of the white star and then multiply by fourth power of the temperature of the white star. Okay, so now it's given that the power radiated by the white star, that is PW, that is equal to PR. So it's given in the statement of the question. So that means now we can equate equation 2 and 3. Okay, so that is, we can rewrite here RW square TW, sorry, this is W, TW 4, and this is equal to R square and TR power 4. So when you rearrange this equation, so from here we can write TW in terms of TR. So TW will be TR multiplied by RR upon RW, and then its power 1 by 2. Okay, So now we will check all these 4 conditions that and try to figure out which one is going to be correct. Okay, so based upon this relation we will try to figure out. Okay, so if let's continue with the first option, that is option A. If we assume that R, that is radius of the red star, if this is greater than RW, okay, and then try to figure out from the equation 4. Let's call this as equation 4. Okay, so when RR it's larger than RW, so when RR here it's larger than RW, so that means this quantity it's going to be larger than unity. Okay, so that means TW is going to be greater than TR. So this condition, when RR it's larger than RW, this implies that TW will be larger than TR. And if you take a look at the option A, it's given that when RR it's larger than RW and TR is greater than TW. Okay, so that means option A is incorrect. So option A, that is incorrect. So this is in fact the correct this condition implies that TW is larger than TR. This is the correct one, but the option it's written in a wrong way, so therefore option A is incorrect. Now let's try to take a look at the option B. What is given in the option B? When RR is less than RW, so that means when RR this is less than RW, so this implies what? So when here let's take a look at equation 4. When RR is smaller than RW, so that means we will get a quantity in the under root which is smaller than unity. Okay, so when we will take its under root, that will be a quantity smaller than unity. Okay, so that means this will imply that TW is smaller than TR. So this will imply TW is smaller than TR. Okay, so what is given here in the option B? When RR it's smaller than RW, so this will imply that TW is smaller than TR. So that means option B is correct here. Okay, now let's take a look at option C. Option C. What is that? When RR is larger than RW. So RR greater than RW. So this implies, so if we have already done this correctly in option A. So when RR is larger than RW, so this will imply TW is larger than TR. TW is greater than TR. So what is given in the option? So when RR it's larger than larger than RW. It's not R here, what? RW. Okay, this is RW. Okay, RR greater than RW, so that is RR greater than RW. This will imply that TW is larger than TR. So yes, this is all. So here it's also correct. Okay, now let's come to the option D. Let's check whether it's correct or not. Option D, what is? When RR is smaller than RW. So when RR it is less than RW. So we have already analyzed this option in option B. Okay, so this will imply that TW it is less than TR. What is given in the option? TW is greater than TR. So that means option D is also incorrect. So here I just want to emphasize here that here, because this question was asked with the only one option correct, but here the way they have given the option, so here option B and option C, they are correct in my opinion. So B and C are correct. The statement is, a thermodynamic system is described by the PVT coordinates. Choose the valid expressions for the system. So here, before we continue with the description of this problem, so let's try to understand the reciprocity theorem. Because if we understand the reciprocity theorem, then we will be able to figure out which one is the correct option. So this question, it's a MSQ type question having more than one option correct. Okay, so let's try to figure out which are the correct one. Okay, okay, the reciprocity theorem says that if we are having 3 variable x, y and z, so I can write dx by dy at fixed value of z. Okay, I can rewrite this to be equal to minus dx upon dz. Now keep the third variable constant. What is the third variable? It's y. Okay, keep y constant and then dz upon dy. Now bring the third variable, which is x, but don't forget to put a negative sign here. So this result is called as reciprocity theorem. So now we have to make use of this theorem, and we have to identify which one is going to the correct option. Okay, so now let's continue with the option A. Okay, so in option A we are given dp by dt at constant volume. So I'm starting with the right hand side. Okay, dp by dt at constant volume. Okay, and this will be equal to negative sign. Now dp by db by dv at constant temperature, and then dv by dt at constant pressure. Okay, and let's take a look whether it's given like this. Yes, so that means in the option it's given that minus dp by dt at constant volume. So it doesn't matter whether you're putting the negative sign on the left hand side or on the right hand side, it's okay. Okay, so that means the option A is correct here. Okay, what's given in the option B? It's the same expression but with positive sign. Okay, so dp by dt at fixed volume, this is equal to the same expression but with positive sign. So that means which is incorrect. So therefore option B is incorrect here. Okay, now let's take a look at the option C. What is option C? This is db by dp at constant temperature, and by using the reciprocity theorem we can write this as dB by dt at constant pressure, and then dt by dp at constant volume. But now we are having a negative sign, don't forget to put the negative sign. So okay, in the option C it's given the same way as we have written here. Okay, so that means the option C is also correct here. Now let's take a look at the option D. So in the option D, the same expression, it's dB by dP at constant temperature, it's given to be equal to this expression but with the positive sign. So that means this is also incorrect. So here option A and option C are correct. So let's take a look at the statement of the next question. The statement is, two gases having molecular diameter d1 and d2 and mean free paths lambda1 and lambda2 respectively, they are trapped separately in identical containers. Okay, so we are given two different gases, okay, and they are trapped in identical containers. So that means the gases, they are confined to same volume. Okay, so let's try to represent the situation here schematically. So we are given two gases where lambda1 is the mean free path for gas 1 and d1 is the corresponding molecular diameter. Okay, and for the gas 2 we are we are having lambda2 as the free path and d2 as the diameter. Okay, and it's also given that d2, this is equal to twice of d1. Now the question is, what is lambda1 by lambda2? Okay, so this we have to find out. So from the theory we know that the mean free path, okay, the mean free path, that is lambda, okay, this is equal to 1 by under root 2 n sigma, where n is equal to number density n divided by volume. Okay, and sigma is what? Sigma is the cross sectional area, or pi d square. Okay, where d is the diameter of the gas molecule. And from here we observe that lambda, that is the mean free path of the gas, this is proportional to 1 by d square. All other parameters, they are constant. Okay, so from here for two different gases we can write, because n that is number density, it's going to be same for the these two different gases. Okay, because they are stored in identical conditions. Okay, so lambda1 by lambda2, lambda1 by lambda2, this is equal to d2 by d1, and it's square because of inverse relationship. So we are given that d2 is equal to twice of d1. So twice d1 divided by d1, it's square, so d1 will cancel with d1, so lambda 1 by lambda 2, that's nothing but that's 4. So therefore this is the correct answer. The statement is a diatomic gas undergoes adiabatic expansion against the piston of a cylinder. Okay. As a result, the temperature of the gas drops from 1150 Kelvin to 400 Kelvin. Okay. The number of moles of the gas required to obtain 2300 joule of work from the expansion is. Okay. So what is given to us? It's an adiabatic expansion. First note that we are talking about adiabatic expansion. Adiabatic expansion. Okay. And then initial temperature is, let's note it as T1. It's given, this is 1150 Kelvin, and the final temperature, because when expansion is taking place, the temperature will drop, so it is 400 Kelvin. Okay. And it's also given that the work done during this process, or we have to basically evaluate the number of moles which are required to perform a work done of 2300 joule. Okay. So we are asked what is n equal to. Okay. So if we recall the expression for the work done during an adiabatic process, W, this is equal to 1 upon gamma minus 1 multiplied by P1 V1 minus P2 B2. Okay, so this is the general expression for the work done during an adiabatic process, where gamma is the adiabatic index of the gas. Okay, so because we are given a diatomic gas, okay, so for the diatomic gas gamma, this is equal to 7 by 5. So we can calculate it from the by knowing the degrees of freedom for the diatomic gas. So for the diatomic gas, the degrees of freedom are 5, 3 translation degrees of freedom, and then 2 rotational degrees of freedom. So from there we can calculate Cv and then Cp, and from those known value of Cp and Cv we can evaluate the value of gamma. Okay, so this is equal to 1.4. Now by making use of the ideal gas equation, we can again transform this information in terms of temperature also. So by making use of this relation, Pv is equal to nRT. Okay, so we can rewrite this equation as this is equal to 1 upon gamma minus 1, or you can say in terms n, I will take nr outside. Okay, and inside we will be left with T1 minus T2. Now with the help of this equation, let's call this as equation 1. By making use of equation 1, we can calculate the value of n. Okay, so remaining quantities, they are given to us. So here W is given as 2300 joule, so that means 2300, this is equal to nr. So n value we have to find out, and r is how much? It is 8.314. it's also given here, that's a gas constant basically, divided by gamma minus 1. So gamma is 1.4, 1.4 minus 1 multiplied by T1, which is 1150 Kelvin, 1150 minus T2, which is 400. Okay, and after solving it, you can easily obtain that n comes out to be equal to 0.1475. Since we are asked to round out the answer up to 2 decimal places, so that means the approximate value of n will be 0.15. So this is our answer.